So as our final speaker for this session, let's welcome Sasha Schmidhuber, who will tell us about Quartic quantum speedups for planted inference.
Okay, thank you very much, Stephen. I'm very happy to tell you today about this work, which is about a new kind of Quartic quantum speedup for a class of problems called planted inference. And this is joint work with wonderful collaborators, with Ryan O'Donnell, who's at CMU, and with Robin Kothari and Ryan Babbush, who are both at Google Quantum AI. And I want to start my talk by kind of motivating why Quartic speedups are interesting in the first place. So it's actually a kind of unusual kind of speedup. Most quantum speedups are either exponential in nature, like Shor's algorithm, or they are quadratic, Grover-like quantum speedups. And exponential speedups are very nice. They're, of course, the holy grail of what we're trying to find when we're trying to develop a new quantum speedup. However, the last 2 decades have just shown that, unfortunately, they're extremely hard to find. Really, since Shor's algorithm, arguably, we haven't found many new end-to-end interesting applications that offer exponential quantum speedups. This is very different for quadratic speedups. Quadratic speedups are very generic. You can get them for pretty much any, for a very large class of problems using tricks like amplitude amplification or related versions. But unfortunately, it turns out that quadratic speedups are likely going to be useless in practice. And the reason for that is due to the very large overheads that come with quantum computing in general, due to things like quantum error correction or just in general slower gate speeds and slower clock speeds. And this is not just me saying this. This was established in several independent studies, for example, in this work by the Google group or in an independent one by the Microsoft group. And they both find that one should really focus beyond quadratic speedups. However, interestingly, both of these papers also find that even if you move just slightly above quadratic, so even if you still have a polynomial quantum speedup, but the degree of your polynomial is slightly bigger than 2, let's say it's cubic or quartic, then this already looks much more promising. So in particular, this Google paper here, it highlights even in the abstract that quartic speedups look much more practical already. And that's exactly what we do in this work. We develop a new quartic quantum speedup. And in fact, what we do is a bit more general than that. We illustrate a very simple recipe for obtaining arbitrary polynomial quantum speedups. And we hope that this simple recipe will find applications even beyond the problems that we study in this work. Okay, let me start by explaining the problem for which we get this quartic speedup. And it's actually a class of problems. It's called planted inference. But for the sake of this talk, I'll just explain one of the problems in this class in detail, which is called sparse learning parity with noise. So here's the problem. Fix some n-bit string z. This is going to be your secret key, and some positive integer k. And you can always think of k as just being 4. That's the smallest non-trivial example. Then the input to k-sparse LPN is you're giving m noisy inner product samples, where m is much bigger than the number of variables n. Okay, so what it means, what a noisy inner product sample is, it has each sample has 2 elements. The left-hand side is Si, which is some uniformly chosen random k-sparse vector. And the right-hand side is just the inner product between your secret key z and this randomly chosen uniform vector Si. Added with some Bernoulli noise, epsilon I, which is just bit noise, which is with 99% probability it's 0, and with 1% probability it corrupts the inner product bit. So it's 1. Okay, so this is the input. It's m of such noisy inner product samples. And the goal, the task given this input is to simply recover z, to find this hidden key z. So this is, it's certainly a problem, but why should you care about it? Turns out it has a very long history. It's been studied for over 40 years, which is, in CS, it's quite a long time. It's studied as the key example of the average case hardness of random constraint satisfaction problems. It's also very closely related to the two key contenders for post-quantum crypto, which are LPN, so just exactly this problem, but dropping the sparsity constraint. It's called learning parity with noise. Or learning with errors, which is basically LPN, but instead of F2, it's over very large prime fields, FP. Now, because of this, sparse LPN can be used to obtain a lot of important cryptographic primitives. So you can use it to obtain pseudo-random generators or lossy trapdoor functions or things like public key encryption. But even beyond crypto, this problem, the hardness of this problem of sparse LPN is very closely related to the hardness of sparse CSPs, so sparse constraint satisfaction problems, and thus to the hardness of combinatorial optimization. One example of such a sparse CSP is KXOR, random KXOR, planted KXOR. And if you prefer physics language, that's a random spin glass. Okay, so here what we achieve for this problem, which is we achieve a quartic degree 4 quantum speedup over the best known classical algorithm for solving k-sparse LPN. And additionally, our algorithm achieves an exponential speedup or an exponential saving in space over that same best known classical algorithm. And we achieve this based on prior work by Matt Hastings, who developed a related quantum algorithm that also achieves a quartic speedup for a different problem called tensor PCA. And we simplify this algorithm and at the same time generalize it to apply to this larger class of problems called planted inference. How we do this in general is by quantizing a class of classical algorithms called the Kikuchi method. And we achieve a quartic speedup over any problem where the best classical algorithm is based on the Kikuchi method, which in particular includes tensor PCA, but also sparse LPN and other problems. And I would just, on this results slide, say once again that because sparse LPN is actually used to construct these cryptographic primitives, are better than expected, better than quadratic attack, suggests that some of these cryptographic schemes might have to increase their security parameters. Okay, so let me explain how this quantum algorithm works. And I'll start by explaining the underlying principle of how we get this quartic speedup, which is called the guided sparse Hamiltonian problem. So almost any problem in any algorithmic task you can rewrite as trying to estimate the ground state energy of some sparse or local Hamiltonian. And this is a very general problem. It's a very hard problem. It's the canonical QMA complete problem. So you don't expect to solve this efficiently on a quantum computer. But there is a way to make this problem much easier, which is if someone gives you a guiding state that has very good overlap with the ground state whose energy you're trying to estimate. So let me make this precise. Let's say you have an n-qubit system, and someone gives you a guiding state psi that has inverse Pauli overlap with the ground state whose energy you're trying to estimate. Turns out then there's a very simple, efficient quantum algorithm for estimating this ground state energy up to inverse Pauli error, which is just quantum phase estimation. Right? You use as your initial state, you use this guiding state, you apply quantum phase estimation many times, and because the overlap between the guiding state and the ground state is very good, you'll find the ground state energy after polynomial repetitions. However, the same problem, even given access to the guiding state, is still exponentially hard classically. And this was shown by proving BQP completeness by Garibian and Legal, and then later improved by Chris Cade and others. So this problem I wrote down here, it's a sort of a very nice abstract framework for getting exponential quantum speedups. But there is, of course, a very big caveat here, which is someone has to give you this guiding state. And it's very much unclear where this guiding state comes from in any practical applications. So I think it's fair to say there's not a single natural problem where you can provably prepare a guiding state that has such good overlap with the ground state in an end-to-end fashion. Of course, for any natural problem, excluding such an abstract problem written down here. Now, the central claim I want to convince you today is that this changes drastically if you relax the condition on how good the overlap between the guiding state and the ground state has to be. And in fact, you can use this idea to still get polynomial quantum speedups for this class of problems called planted inference. So we claim that planted inference problems naturally instantiate what's called a fine-grained version of this guided sparse Hamiltonian problem. So that means two things. It first means that the best classical algorithm for solving these planted inference problems already works by mapping it to the ground state energy estimation problem of some exponentially large, yet implicitly defined sparse Hamiltonian. Okay? And moreover, for this kind of structured Hamiltonian that you get for these problems, there is a guiding state that has improved overlap with the ground state. And that guiding state is efficiently preparable, giving just the input of the problem and nothing else. And what do I mean by improved here? So it's no longer, the overlap with the ground state is no longer inverse polynomial. Instead, it's exponentially small, but it's 1 over the square root of the dimension of the space. And that is quadratically improved over what you would naively expect. So something you can always do is you just pick some random guiding state. You use a fully mixed state as your guiding state. And then the expected overlap would be 1 over the dimension. But we're claiming that for planted inference problem, you can do quadratically better than that. And this overlap, this improved overlap, is really the source of our Quartic speedups. Why is it Quartic? We combine 2 quadratic speedups. So first, the algorithm is just, again, construct the initial state, the guiding state, and repeatedly apply quantum phase estimation until you find the ground state energy. And you get a quadratic improvement because your initial state has good overlap with the ground state. And you get another quadratic improvement because you can just apply amplitude amplification on top of that. So our Quartic speedup is a combination of 2 quadratic speedups, one from the overlap of the guiding state and one from generic amplitude amplification. Okay, so this is just a sort of high-level overview. If I want to flesh this out, I really have to explain 2 things to you. One is, okay, what is this Hamiltonian whose ground state somehow encodes the planted secret key Z of the sparse LPN instance? And the other thing is, okay, where does this guiding state come from? And I'll start with the Hamiltonian. And this Hamiltonian, it turns out, it's some object that classical computer scientists have studied before us. It's called the Kikuchi method, or the Kikuchi matrix. And this is a method developed by Wine and others in 2019, and then independently discovered by Hastings in his tensor PCA paper. And I'll just sort of very briefly explain what it is. It's a way of taking a degree k optimization problem and reducing it to a degree 2 optimization problem. Okay, so it takes a hypergraph problem to a graph problem, or say a tensor problem to a matrix problem, or a k-sparse LPN instance to a 2-sparse LPN instance. And the reason why this is nice is because degree 2 optimization problems you can attack with spectral methods, which are very fast and reliable. So in a little bit more detail, the Kikuchi method is a hierarchy. For any L, there is a Lth order Kikuchi method, which takes a sparse LPN instance and maps it to some large sparse Kikuchi matrix of dimension n to the L times n to the L. And the central promise is that if you choose L large enough, which in the case of sparse LPN means polylog in n, then the ground state of this Kikuchi matrix encodes the planted string Z, this planted key that's hidden in the sparse LPN instance. And there's an extremely nice interpretation of this fact in terms of mean field theory and statistical physics. It turns out the Kikuchi method, it has an interpretation as the mean field Hamiltonian of an L particle system. And as you increase L, your system gets better and better described by mean field theory, meaning the correlations between the individual particles dies out. And this, on a high level, is what allows you to encode this planted Z in the ground state. But I don't have time to get into this. If you have any questions about this, please ask me after the talk. Okay, so that's the Hamiltonian. What about the guiding state? Again, the key observation that gives us the speedup is that for this Kikuchi method, for this Kikuchi matrix, there exists a guiding state that has quadratically improved overlap with the ground state of the Kikuchi matrix, quadratically improved over a random state. And I'll give you some very brief intuition for what this guiding state looks like. So recall that we're given as input to our sparse LPN instance m noisy inner product samples, which is a combination of a k-sparse vector and some bit, so noisy inner product bit. Now, we want to find z, this planted key. And I've just written z here as a quantum state. It's an n-bit string, so I can write it as a superposition of n quantum states, where the phase encodes the ith bit. Finding the c is pretty much equivalent to finding its k-fold tensor product. And you can easily convince yourself that this takes the form as I wrote down there. It's just, you can write it as a superposition over k tuples, where the phase of some k tuple s is defined by the inner product of that k tuple with the planted key z. So this state at the very right, right for you, is the state you want to prepare. Now, of course, you don't know z's or you don't know all these phases, but you do have very good guesses for them in some cases. And that is whenever the 4 tuple happens to describe the non-zero elements of one of these 4 sparse, anytime I say 4, I mean k. Of this k-sparse left-hand sides, these randomly sampled vectors of the sparse LPN instance, then you actually know what this inner product is up to this Bernoulli noise epsilon. So what you can do, given just sparse LPN equations, you can prepare some m sparse state, which is a superposition over 4 tuples as well, but only those that appear in the instance. And the phase is defined by this noisy inner product sample. And if you just look at the overlap between those two states, the c to the k that you're trying to find and this guiding state psi, the signs match whenever they match in 99% of the cases when there's no noise, and they don't match in 1% of the cases when there is noise. So you get a lot of constructive interference here. And if you just do the math and look at how big this overlap is, it turns out to be quadratically improved over what you would get for a random vector. So this rough idea is the source of our quadratically improved overlap. As you can see in our paper, there are more ideas like symmetrization that actually go in the guiding state we actually use. Okay, so far I've only talked about sparse LPN. Let me say that this method also works for other planted inference problems. One of them is tensor PCA, which is a problem originally studied by Hastings, which actually inspired us to do this work. And we show that we recover Hastings results and also get a Quartic speedup for tensor PCA using our algorithm. And then there are other planted inference problems, like community detection, or planted hyperclique, or planted clique, or group synchronization, which is really the mother of all these planted inference problems. And we anticipate that you can also get Quartic speedups or similar polynomial quantum speedups for these problems, but we don't study them in detail in our paper. Okay, so I'll wrap up. Just to summarize, we do 2 things in our work. We quantize this classical algorithm called the Kikuchi method, achieving a Quartic quantum speedup for any problem where the best classical algorithm is the Kikuchi method. And that includes k-sparse LPN, it includes tensor PCA, and it potentially includes also other planted inference problems and random CSPs. And the way we get the speedup is by illustrating that planted inference problems naturally instantiate what we call the fine-grained version of this guided sparse Hamiltonian problem. And this is really quite remarkable. It means that all this fine print that has to be satisfied usually for quantum algorithms to get end-to-end speedups, it is satisfied for planted inference problems. And I've listed the fine print here again. So the best classical algorithm corresponds to finding the ground state of some matrix that is very large, yet sparse and implicitly defined. And for this Hamiltonian, you can construct a guiding state given just the input of the problem, which has improved overlap with the ground state space. So thank you very, very much for listening.
Thanks for a nice talk. So I guess you're saying that this part of the Quartic is coming from having these very nice guiding states, and then I guess you also seems to hint that this structure is very present for this planted problem. But like, could you explain a bit kind of why? And like, you know, are you saying that this kind of is just very common in planted problem, or how to find other place where this guiding state could, you know, have this like better than random guessing kind of behavior?
Is the question why planted problems have an easy to extract guiding state? Or?
Yeah.
Okay. Yeah, I mean, it's not. This was sort of the key observation by Hastings. It's hard to give like a meta reason why, why this should be true, except that, as soon as you have a plant, that plant itself is a natural candidate. Like any information that you can get towards where this plant is directed is a natural candidate for a guiding state. And then the question is, what information are you giving in the input of the problem? Is it actually enough information to get a meaningful speedup that's better than superquadratic? And it turns out that for sparse LPN and for tensor PCA, that is true. But it's a question that you have to ask, that you have to investigate for any planted inference problem. And I've written down a few other problems where I think it's true, but we haven't sort of looked enough into it yet to prove that.
Thanks.
Hi, Sasha. So is the n squared times n squared like also a lower bound, or have you looked into proving that it's actually a lower bound? Like the faster version divided by n to the fourth, that is.
Yeah. So, yeah, I mean, we don't have a proof that this is a lower bound for the quantum case. Yeah, you could improve this. For the classical case, there's an implicit question, which is, okay, for the classical case, is the quantum algorithm for which we get a speedup actually the best classical algorithm? Are there classical lower bounds there? And there are lower bounds there. There are sum of squares lower bounds. And you can use them to show that the Kikuchi method is nearly optimal. However, these lower bounds are sort of slightly loose, so there's still room for freedom there.
Hello. Thank you for your talk. I have two questions.
Mm-hmm.
The first one is, why doesn't this work for LWE? Closer? Okay.
Okay, so the truth is we haven't tried too hard to make it work for LWE. You'd have to do something non-obvious. If you just try to follow the protocol, it doesn't work. It breaks down for a few reasons. One is the fact that we really use this fact that you're over F2. If the things don't disagree, they add up in a good way, which is no longer true over FP. So there are, the obvious extension doesn't work, but maybe there are some tricks to make it work for LWE.
Thanks. My second question is, you said you have like a fine-grained bound on the guided Hamiltonian. So do you have like a trade-off? Like if you have less noise, then you have an even faster speed up?
If you have less noise, so this is true. I mean, well, the speed up doesn't change, but the whole complexity of the problem changes as you vary the noise parameter. Another thing which is true is as you increase the number of constraints, so this Quartic speedup I've shown you is when the number of constraints is close to n to the k over 2. As you decrease the number of constraints, you have less information in the input, and then your guiding state is going to be a bit worse. And actually, our Quartic speedup is no longer a Quartic speedup as you increase the number of constraints, but it goes down to like 3.9, 3.8, etc. Yeah.
Thank you.
All right, well, let's thank Sasha again for this very nice talk. And that concludes this session. We'll reconvene tomorrow at 9 a.m.